Hello friends, welcome to another tutorial in Analog Electronics series. In this tutorial we'll talk about some basic mathematical operations that can be performed by an operational amplifier. In the previous tutorial we talked about the functioning of an operational amplifier and its gain. That's a special kind of amplifier made out of voltage shunt negative feedback. And we studied the formula for the gain of that amplifier. So if this is something that interests you, then please keep watching. Let's begin this tutorial by drawing the basic symbolic diagram of an operational amplifier that we studied in the previous tutorial. So it consists of an input impedance Z and output impedance Z dash. So if this is V in, so this was the basic idea or the symbolic diagram of an operational amplifier, and the gain of this amplifier was minus Z dash upon Z. Okay, so this is something that we need to keep in mind before we do all the operations that are needed in this presentation. So let's talk about the first operation, which is sign changing or the inverter operation. If we keep Z to be equivalent to Z dash, then what happens? The ratio of AVF becomes equivalent to -1, and this goes to show that whatever input that we're giving at the input is inverted by the operational amplifier without any amplification in the signal. Alright, so that's pretty simple, that we need to keep both the impedances, the input impedance and the feedback impedance, to be exactly equivalent to the same. And the key point here is both the impedance, they need to be resistive impedance. Z and Z dash, they are resistive in nature when we talk about the sign changing or the inverter operation. The next one is scale changer. In scale changer also we keep the ratio of Z dash upon Z to be equivalent to K. So we select the values of the feedback impedance Z dash and the input impedance Z to be such that it is K, a numeric value, a real constant, because then what we'll get is AVF to be equivalent to minus K. So for example, if we choose K to be equivalent to twice, so what we give at the input would be doubly amplified with the inverter sign here. Alright, so that is the scale changing operation. And then we have the phase shifter operation. Phase shifting operation also happens when we keep Z to be equivalent to Z dash, but the magnitude needs to be equal, their phase needs to differ. And how can that happen? By keeping Z and Z dash to be complex numbers. For example, if we keep Z to be equivalent to, let us say, 50 ohms and Z dash to be equivalent to minus 50 j ohm, so that will cause some phase shifting to happen, because their ratio will cause phase shifting other than the 180 degree phase shifts that happens. Okay, then we have the integrator operation performed by the operational amplifier. And how does that happen? In the feedback impedance we use a capacitive impedance, and the input impedance is kept as R. Now this circuit can be reduced to this circuit with a virtual ground here. So this is V input, this is R input impedance, and the feedback impedance is C, and the output impedance is V0. So V0 is minus 1 by C I dt, and I can be substituted as integration of V dt 1 by R. So finally we get the value of V0 to be equivalent to this, which shows the integration operation at analog level. And then we have the differentiator operation, and this can be performed by keeping the input impedance, and this can be performed by keeping the input impedance to be capacitive and the feedback impedance to be resistive. So it is exactly the opposite of the integrator operations. So V0 becomes equivalent to R into I, and then I can be substituted as C dV by dt. So finally we get this formula for the output voltage, which represents differentiation. And it is very important to remember that what is the value of Z and what is the value of Z dash in all these, and how are these symbolic diagrams represented using this virtual ground diagram. This will make the calculations very easy. And finally, what I want to discuss is the adder or the summing amplifier. It is again very simple. In this, what we can do is we can supply 3 different voltages and they combine at this node, resulting in the total current I, and we know this total current enters into the feedback circuit with the impedance R dash. So my I here becomes V1 upon R1 plus V2 upon R2 plus V3 upon R3. Now if all the R's are equivalent to R's, R1, R2, R3 are equivalent to R, then we get the total output voltage to be equivalent to minus R dash upon R, V1 plus V2 plus V3. So this acts as a summing amplifier. So again, very simple operation. Again, this operation is understood by the fact that the current I goes straight into this branch, or the concept of virtual ground, no current goes here. So these were the 6 different mathematical operations that I wanted to discuss about the operational amplifier today. I hope this quick tutorial was of help. If you liked the video, give it a thumbs up, consider subscribing to the channel, and share this video amongst your friends. Till then, take care of your health and stay happy. I'll see you around in the next video to come. Bye bye.